Hello, class. What we're going to now discuss is taking it after we have an epoxide, we can then treat it with a strong nucleophile. Now, we can also react it with a weak nucleophile. So we're going to focus our attention on strong nucleophiles first, and then we'll look at weak nucleophiles. So if we take a epoxide right here, so there's an epoxide right there. And in order to open a ring with a strong nucleophile, let's say if we treat it with sodium amide, all right, you have to do this ring opening process in 2 steps. So the first step is adding the strong nucleophile. Now, why do I know this is a strong nucleophile? Because if we get rid of the metal or the sodium, what does that look like? That is simply an NH2 minus. And strong nucleophiles typically have a formal charge of -1. And then you have to have step 2, which is a acidic workup, like so. And when you do that, what's going to happen is you're going to form a structure that looks like this. Do you see how right here, that is from our strong nucleophile, and this alcohol right here came from the oxygen in the epoxide. So it requires 2 steps, and going through the mechanism will help us see these 2 steps and how they work here. So if we redraw the epoxide here, and in step 1 we have our sodium amide right here. What's going to happen is we have an epoxide. It's a 3-membered ring, so it's pretty strange, so it's reactive. So the nucleophile, or the strong nucleophile, is going to come in and attack one of those carbons like that. Now, if that's the only pink arrow that I draw, I have formed a Texas carbon. So what's going to break is the oxygen-carbon bond right there. So that's the carbon it attacks, so it has to break this oxygen-carbon bond like so. Now that's an epoxide. It already has 2 lone pairs. So when that strong nucleophile comes in, busts that open, what happens is it looks like this. I keep this horizontal bond as is. I just draw it, okay? And then the nitrogen species came from underneath, NH2 like so. And the reason why it has to come in from underneath is because this is a SN2 mechanism. The nucleophile is coming in at the same time. This right here is kind of like the leaving group. That oxygen-carbon bond is leaving or breaking at the same time that this nitrogen species comes in. And so it has to undergo a SN2 style, which is backside attack. And we'll write that down here. Okay? Remember backside attack. And so we have the carbons here, the 2 carbons there. I just have them lined there. The nitrogen came in from underneath, so that means that the O, now these pink lone pairs are already there. But what did we do here? We have 2 electrons right there, which then went there. Now that's an oxygen with a single bond, but 3 lone pairs, so that means that's a negative charge right there. And we still have a lone pair on that nitrogen. So that's the first step in opening up an epoxide, an SN2 style reaction. Then the next step right here is the aqueous workup, or no, more accurately, the acidic workup. So we have our hydronium right here, and that's going to be our acid. And we have a strong base right here, negatively charged oxygen. So that's going to come in, grab that proton, and give us our product. Like so. Plus what? We just took that proton, so now we have water left over. Just like that. Now it looks like I've cut off a little bit here. So let's fix that final product here so you can see it. We'll go, I'll try to make it a little bit smaller here. Is that better? No, still cutting off. So I'm going to draw it down here. Let's see if that's, oh boy, struggle today. So let's do it this way then. Okay, we'll go right there. Like that. Okay, so that's our product plus the water. And that is going to be our second step. So that's step 2 from here all the way to there is our second step. Okay. So the reason why we need this acidic workup is because we have the alkoxide right here, and we have to protonate that with some acid to get us our product right there. Okay. Now, in this particular example, I showed you the sodium amide, but any strong nucleophile could be used. So some examples of some strong nucleophiles could be, let's say, sodium hydroxide. So that is what? Just the hydroxide. That's our, like that. So if we did sodium hydroxide instead of sodium amide, what would our product look like? We just go and go like that. We could have a thiol, so Sr minus, like that. What would that look like? Well, kind of just like the hydroxyl, SH. Wait, that's an R. Sr, like so. So you see the trend here. So what if we had sodium cyanide? Right there. Or we could do sodium OR. So that, and that looks similar, and it would behave similarly. So another interesting one that's a little bit different than these that I just drew is a Grignard and a lithium aluminum hydride. So if we treat this with a Grignard, so maybe we should clean this up here. Yeah, let's clean this up. So if we take a look at a Grignard reaction, what would the product look like? It would turn into that species right there. See the R right there? Would go there. Because remember, Grignards, you could look at it this way. You could draw it out, and the Grignards can act as a nucleophile, like so, to give us that product, overall product. Remember, though, the first step turns it into an alkoxide, and then you have to use the acidic workup to protonate the alkoxide to turn it into an alcohol. What's another species that kind of resembles that? The lithium aluminum hydride. Aluminum hydride, like that. And remember, hydrides, shorthand, we could just draw them like this. All right, and so that that lone pair right there is going to come in and attack. And what's it going to do? It's going to add a hydrogen. But notice that right here, there's already 2 hydrogens. So we've added a third hydrogen to that carbon from the lithium aluminum hydride right there. Okay, so those are some examples of strong nucleophiles. Now, your epoxides can look a little bit more complicated. Okay. And so now what we have to address is regiochemistry or regioselectivity here. So if we have an epoxide that looks like this, okay, and we have two methyls coming off here, can't see that other methyl there. So, okay, so I have two methyls coming off of here. There's our epoxide, and let's say we treat it with sodium hydroxide. No, sodium amide, let's do that. Okay, in step 1, and then in step 2, we add our acid workup there. So it begs the question, what product am I going to get? Am I going to get this one? So the two methyls there, and then our amide, or sorry, now our amine, like that, versus are we going to get it like this? Do you see the difference in those two compounds? If I number that carbon 1 and carbon 2, carbon 1, carbon 2, do you see the difference between these two compounds? It's regioselectivity. This nitrogen species, which carbon is it going to prefer to attack? Carbon 1 or carbon 2? And in order to make this judgment call, which one is going to work, is we have to understand what we talked about previously. What type of mechanism did we go for or invoke when we were using strong nucleophiles? We were saying, hey, this is going to be an SN2 style reaction. Look at that carbon right there. So in this situation, remember SN2s where you have a alkyl halide? If it's a primary alkyl halide, SN2 goes very, very fast and does very well. But if it's a secondary or more importantly, a tertiary alkyl halide, we don't undergo SN2 because it's just so unstable, right? And that was horribly drawn. Draw it more like that. So based off of what we know about SN2 reactions, and based off of sterics, when this nucleophile right here, the sodium amide, comes floating in, there's all these methyls right here, which are nice and bulky. And so this amide is going to be like, hey, I can get to carbon 2 a whole lot easier. So it's a steric argument. So when your epoxide is in its neutral form, the strong nucleophile is going to prefer the carbon that is less substituted. And you can see carbon 1 has 2 methyl groups, whereas carbon 2 only has 2 hydrogens. So it's less substituted, so it goes for carbon 2. So our product, our major product, is going to be this guy right there. And our preferred product. And we can rationalize that choice or that answer due to sterics and that it's an SN2 mechanism. Okay. Now there's another aspect to this. Well, let me back up. Now what I'm talking about here, I mentioned that when your epoxide is neutral, you can, and we will see it shortly, we could have the exact same epoxide drawn here that looks like this, where I protonate the epoxide. When the epoxide is protonated, the carbon that the nucleophile attacks is going to be different than when the epoxide is neutral. And that oxygen right there is neutral. The strong nucleophile is going to go to the least substituted carbon. And I know I've said that like 4 or 5 times, but It's so important because when we start looking at epoxides that look like this, the trend is opposite. Okay? So let's not dwell too much about this one quite yet. So the next thing, so we've discussed regiochemistry. Now the next thing is stereochemistry. So let's take a look at a cyclohexane ring right here. And I'm going to draw the epoxide looking like this. All right. Now, do you see how this epoxide, they're both wedges. They're coming out of the board. And let's put a methyl group right there. Okay. So when we treat this with a strong nucleophile, and we could represent that strong nucleophile like this if we'd like. Okay. Now, based off of what I just taught you, there's carbon 1 and carbon 2. When this nucleophile wants to open up this epoxide, okay, which carbon is it going to attack? Well, you see that the epoxide right here is neutral. So the strong nucleophile is going to attack the least substituted carbon, and that would be carbon 2. All right. So that's the regiochemistry part. The oxygen-carbon bond right here has to break, like that. And so that's regiochemistry, but stereochemistry is going to say, hey, do we have wedges and dashes? And so you see that the nucleophile did not touch carbon 1 at all. So the stereochemistry at carbon 1 is not affected. It does not change. So it still has the dashed methyl, and it still has the wedged alkoxide, which in step 2, that alkoxide is going to be protonated with the acidic workup. So we could just say, hey, that's going to turn into an alcohol after the second step. But this nucleophile that attacked carbon 2, we cannot just say, hey, the nucleophile attacked carbon 2. Because if this was your answer, it's partially correct because you selected the right you figured out the regiochemistry, which said, hey, we go to carbon 2. But is this nucleophile a wedge or a dash? There's stereochemistry. There's a stereochemistry component to this. So it all goes back. What is the mechanism that we are invoking here? That is a SN2. So that's a backside attack. And so where's the leaving group? It's that wedge. And so it's a wedge. So it's on the top or the front face of the ring. So that means the nucleophile has to attack from the opposite side or backside attack. So it's going to approach this ring from the backside. All right. So do you see how it's a wedge here? But when the nucleophile comes in, it's doing SN2, backside attack, and so it comes in from the backside, which gives us the dash. And so that's the stereochemical outcome of what's going on here. So let's do another problem about this concept and kind of wrap it all together. Now let's compare this molecule that we just looked at. Do you see now in this representation, the epoxide is wedges right here? But then in this representation, the epoxide's in the plane of the glass. So you can represent this in both ways. So if we take this species right here and treat it with the sodium amide, sodium cyanide, what would we have here? It would come in backside attack, like so, and give us our product that looks like this, right? like so, okay? Now contrast that to when the epoxide's in the plane of the glass. And so we'll take our cyanide right there and watch what happens here. We're going to come and bring in and do SN2 style backside attack, right, like so. Now here's the trick, class. You take this carbon 1, carbon 2, just draw, okay? And then you will look at all these groups here. Now, why did this cyanide attack this carbon? Because it's less substituted. It has a hydrogen and an ethyl, but this carbon over here has an ethyl and a propyl. So it's more crowded over here. That's why it chose that carbon. So all you have to do is, if the cyanide comes in from underneath, and it has to come in from the opposite side as this carbon-oxygen bond is breaking. So that means that you take your cyanide and stick it underneath, CN right there, and then you keep these wedges and dashes exactly the same. Don't change it. So we have a wedged hydrogen and a dashed ethyl. Just write it down. And then it's the oxygen carbon bond breaks. The oxygen is going to be on the opposite side, right here, of the cyanide. But then these groups right here stay exactly the same. Ethyl and propyl. Okay. And then step 2 would protonate that alkoxide to get us our alcohol. Okay. Like so. And now that is going to be the proper stereochemistry. But one thing that you need to be aware of, okay, is that we have free bond rotation around there. So your answer, that is the correct answer, but when you look at a multiple choice test, this answer choice it will be on the one of the answer choices, but it may not look like this. It may take this carbon-carbon bond right here and spin it and rotate it into a different conformer. So I would recommend taking this product right here and just rotating around this bond right here and looking at what the different conformers would look like, so you can get an understanding of what's going on here. Okay. So why is that so important here? Because what did we generate here? What do we have? We have a stereocenter. And so if we have a stereocenter, is it R or S? But look at this, an interesting thing here. That carbon right there, that's a stereocenter as well, right? And so what happens when you do an SN2 reaction at a stereocenter? You invert the configuration, right? Okay, so let's, yeah, that's where we'll stop there, okay? So next, what we want to take a look at is looking at epoxides that are now protonated. So we're going to take a look at epoxides that have different substitution patterns on the carbons, but that are also protonated. And we want to take a look at how the nucleophiles interact with that type of epoxide. So let's take a look at an epoxide right there. And if you treat it with an acid like HCl, HBr, HI, right, we treat that with that acid right there. What are we going to get? We're simply going to get that. And how it happens mechanistically is that we have an oxygen atom right here. That has a lone pair. We have acid, so that lone pair is going to come in here and grab ourselves a proton. When it grabs that proton, it's now going to be a positively charged or protonated epoxide. And when it's protonated, it weakens this oxygen-carbon bond a little bit more than it was when it was neutral. Okay? And so that's going to help our plus our conjugate base right here. All right. And so now our conjugate base right here can act as a nucleophile and attack the carbon like so to give us our product. And so it would look like this. OH, like so. Okay. So that's the mechanism for treating an epoxide with our HX. Okay. Now we can also do this with water with a little bit of acid. Okay. So let's say if we treat it with sulfuric acid, SO4, and water. All right. What's the major product going to be? Well, whenever you have sulfuric acid and water, that basically means that you have hydronium. Like so. All right. And so the first step, what's going to happen when you mix these two reagents together is it's going to form the hydronium, and that's going to protonate the epoxide. So if we go down here, our epoxide will then get protonated right there, positively charged. But what do we have left over after the hydronium gets one of its protons ripped off? We have water that's left behind. Okay. And so water is now going to come in and attack like so. But pay very close attention what's different about this mechanistic step than from the previous example. Look at what happens here. OH. Am I cut off? Okay. So, do you see how this water molecule attacked that carbon? So this water molecule is now here. Do you see how it still has the two hydrogens that are right there? And so in this, when you're using sulfuric acid and water, you have one additional proton transfer step. And that is, okay, we're still going to have a lot of water present. Okay? So we're going to use that water as a base to come in to protonate that. And so now that's going to give us our alcohol there and our alcohol there. Plus, it regenerates our hydronium, hence acid-catalyzed. We regenerate the catalyst. And you can generate your diol right there. So you can do this also. Look at this, it's pretty slick. You can also do this with an alcohol. All right. So if I replace one of those hydrogens right there and replace it with a R group like that. Okay. So what you're going to generate here is something that resembles, and I'm gonna draw it right off of that R right there, right? And so this would be H R like that. So when you take a alcohol and treat it with sulfuric acid or another acid, what you're going to do is you're going to protonate that alcohol. Do you see how we've tacked on an additional? So let's redraw it here. trying to save space, but it doesn't seem like it's working too well. So what we have is the original right here, and then we are going to protonate it with one of the hydrogens from the acid. So here's our protonated alcohol, okay? And so the epoxide is going to come in like it's shown here and grab one of those protons. So now we have a protonated epoxide, and now we have our alcohol again. So from here to here, we got it back. Now that alcohol is going to do a nucleophilic attack, SN2 style. Okay. And then what's going to change here? This will be my R right there. And this will be my R right there. All right. So look, what kind of functional group do we have right there? That is an ether. So my point is you can use sulfuric acid with water, and you can use sulfuric acid with an alcohol, and the mechanism is the same. All right. Very same mechanism there. Now, let's take a look here. Let's do a compare and contrast now. Sorry. Just trying to think how I want to talk about this here. So let's take a look at an epoxide that looks like this. All right. And we'll put in our two methyl groups right there. All right. And if we treat it with let's say hydroxide, step 1, and step 2, we do our acidic workup. What's the major product going to be? Well, it's going to be, let's see here. And this is the type of problem we've seen before. We have steric effects. These two methyl groups don't allow the hydroxide to come and attack that carbon. So it's going to attack at carbon 1. So our product is going to look like this. There's our methyl, and then we would have OH like that. All right. So that's our product. But what if we took that same epoxide, okay, like so, and treated it with water, H2O, and sulfuric acid? What would our major product be now? All right. You know, let's see. Let's change this up so you can actually see the difference here. So let's go OR. And so there's our OR. And we will do the same to this side. We will do it with that. Okay. Now look at the difference here. When we treat it under acidic conditions in the first step, do you see how in this reaction there's 2 steps? Here it's just 1. And so what's going to happen is our intermediate is going to look like this. there's our protonated epoxide. And so where is our alcohol going to attack? It is going to attack at carbon 2. Now let's draw that product in a different color. So our answer for this reaction in the bottom right here is going to be this. We would have boom, boom, OR, OH, like that. Now comparing this pink one and this green one, do you see the difference? Where did the OR attack? On the top one, it attacked at carbon 1. And in the green molecule, it attacked at carbon 2. So there's a difference in regioselectivity here. So what we have going on here is we have steric effects, which is important. And we still have steric effects here, or should I say right here. But there's another factor that is more important than steric effects, and that is called electronic effects. Okay. So when we have a protonated epoxide, we're going to invoke electronic effects to determine which carbon is going to get attacked by the nucleophile. And notice that in this bottom reaction right here, we are using a weak nucleophile, whereas in the reaction up top, we're using a strong nucleophile. Also, another difference, when we're using strong nucleophiles, the epoxide is neutral. And when we're using weak nucleophiles, the epoxide will get protonated. And that's going to determine the regioselectivity here. Now let's talk more about the electronic effects here and what's going on. Right? So if we have a protonated epoxide, what is interesting here, if we go here like that, when it gets protonated, this oxygen carbon bond gets weaker. Okay? But which one gets weaker? We have this one right here, and this one gets, and we have this one over here. So only one of them gets extra weak. Okay? So what we have is this oxygen carbon bond is the one that's going to be the weakest because, let's just do a hypothetical. What if I completely broke that oxygen carbon bond? That's not what happens, but what if I just completely broke it? So it would look like this. Okay, if I just completely broke it and put the electrons on the oxygen, I would get a carbocation, all right? But what if I broke the other one? What if I went more like, and I broke this carbon-oxygen bond? What would we have? We would now have a primary carbocation. So when the protonated epoxide is making the decision on which bond to start breaking first, or no, which bond it wants to start to break, it's going to choose this one because it has a partial positive charge, a greater partial positive right here. All right? So I'm going to draw a large partial positive for this carbon and a tiny partial positive. This bond right here is going to be partially broken because it's going to generate a more stable partial positive due to this idea right here. Okay? And so how we kind of draw this is we can draw it like this. And going to draw more like, darn it, draw more like this. I'm going to draw the hydrogen right there for right now. Right. So this molecule right here, I'm drawing it like this. And so what you're seeing is this bond right here is going to be longer and breaking. And I'm representing that with that dotted line. And so what happens right here is that this is going to be a whole lot larger partial positive than this one. That one's larger. And so when we have our nucleophile floating around, which was our alcohol, this lone pair right there is going to be attracted to which carbon? It's going to be attracted to the one that's more partially positive. And so it's going to go for this carbon. And it goes by the same mechanism, an SN2. So what happens here is this alcohol right here, which is a weak nucleophile, is going to come in SN2 style, backside attack, and generate our alcohol, our ether right here, and our alcohol there. And then we do another proton transfer to get rid of that proton. And I'm just going to skip that mechanistic step because we've already gone through it to generate that species. So it's another SN2 style mechanism, but people should be freaking out right now. How can a nucleophile attack a tertiary carbon right there? Because look at that circled carbon right there. That it has 1 carbon, 2 carbon, 3 carbon. So that's a tertiary carbon. And we've learned that you cannot do an SN2 reaction on a tertiary carbon. But why am I saying you can now? And the reason why it is allowed for an epoxide to occur is because of this effect. So when I draw the molecule like this, that center right there looks like it's tetrahedral, okay? And so if it was completely tetrahedral, this could not come in and attack. That's what we've learned previously. But if it looks more like this, because this oxygen-carbon bond is breaking because it's not very stable, then this carbon right here, the one that the alcohol is going to attack, is not completely tetrahedral. It's more planar. So it's like in between. This carbon isn't 100% tetrahedral, and it's not 100% planar, but it's enough, it's different enough that for this alcohol to be able to approach and attack. So in summary, what we have going on here is that when you take a look at this epoxide, people may think the alcohol can't go to that carbon because of sterics. But there is a feature or a phenomenon that is more important than sterics, and that is right here, the electronic effects. And because the electronic effects are more important, this alcohol is going to go to the more substituted carbon. So that is the principle that we could say. If you have an epoxide, if you have a neutral epoxide, the nucleophile is going to attack the least substituted carbon. So in this particular example, the nucleophile would attack carbon 1. But if you have an epoxide that is protonated, right here, the nucleophile is going to attack the more substituted carbon. So if we number those, the nucleophile will attack at carbon 2. So that's, if you can understand and remember that, you're good. You're going to be able to answer most of the questions. The other layer of understanding is, can you explain why this works? So yeah, you need to understand this, and some people may just memorize it. But on a free response question, if I ask you why or how this works, memorizing this information is not going to allow you to answer those types of questions. So I encourage you to understand this at a deeper level and understand the theory and the principles behind it. And if you can do that, then you'll be a whole lot better off, and you'll be able to study for those standardized exams. So under the acidic conditions here, let's look at another example here. The same principle applies when it comes to stereochemistry here. So if I have an epoxide that looks like this, okay, and let's draw in our methyl group right here. And let's say we're going to treat it with some sulfuric acid and an alcohol. What kind of alcohol do we want to do? Let's do ethanol. Okay. Now, sometimes the textbook uses sulfuric acid, or sometimes it just says, hey, we're going to add an H+. So that tells us that we're dealing with an acid, right? So then what would our product be? Well, we're under acidic conditions. So that means one of the intermediates here is going to be a protonated epoxide, right? So if we have a protonated epoxide, where's our weak nucleophile going to attack? And our weak nucleophile here is our alcohol. So is it going to attack carbon 1 or carbon 2? Well, this is protonated, so that means the weak nucleophile is going to attack the more substituted carbon, right there, okay? Now, when that attacks, it's going SN2 style, so that means this carbon-oxygen bond right here has to break, like so. And so what's the stereochemical outcome of this? Well, this ethoxide is coming in from the back side because the leaving group bond right here, the carbon-oxygen, is in the front. So if we redraw that, so that means we have our alcohol there. Do you see how this carbon-oxygen bond was not affected from the nucleophile? So that wedge stays. And that wedge is bonded to that oxygen, and that oxygen is bonded to that hydrogen. So that's there. Now we're invoking an SN2 here, and so that means that the ethanol is coming from the back side. So that means that's going to come in like this. And it has the hydrogen right there. So if the ethanol comes in from the backside, that's going to now be protonated when it forms that oxygen-carbon bond. But where did this methyl group go? It's still there. But now look at what type of bond it is. It is now a wedge right there. Because this ethoxide came in from backside, which then pops that methyl group to a wedge. And then what are we going to do? We will do we'll do a proton transfer. And so we will take some of our ethanol right here, and that's going to come in and grab that proton, break that oxygen-hydrogen bond to give us our product. And our product is going to be right here. There's our ethanol. Not cutting anything off yet. Okay. So there's our wedge. Messy looking wedge, but it's still there. And then we have our methyl group. So that would be our product. So you see, we have regiochemistry. Where's the ethanol going to attack? It's going to attack the more substituted carbon because we're under acidic conditions, because we have an acid will then protonate that epoxide. And then we have our stereochemical outcome that we need to account for. And we know that it's going to attack SN2 style, so that's going to invert the stereochemistry of these groups. All right. How much time do we have? Okay. Okay, class, that looks like that's a good place to start. And in class, we will wrap it up by talking about thiols and sulfides and how they react. Okay, as always, if you have any questions or concerns, please reach out. I'm more than happy to help. Come to office hours, talk to our TAs, talk to our graduate students. They're there to help you. Okay.